All right, everyone, let's get started. So today we'll have a lecture about sort of in this distributed system theme in the class. And we're going to talk about this paper I4 that's really looking at the problem of protocol verification. And you can think of protocol verification as really being a subset of verifying distributed systems. We'll look in a second as where this I4 technique or idea sits in relation to the big picture of what you might want to do in a distributed system. But roughly, the reason we think this is an important problem is that it is actually a somewhat hard problem to verify a protocol to be correct. And one nice thing about it is that it's really a reasonably separable problem. What I mean by that, it's really separable from the software that is implementing a protocol. And this is something that we basically saw in the Amazon paper in the first week of class, where the Amazon developers really thought that it was difficult to verify the protocol separate from how they were going to implement this. And this is sort of in the same space that this paper is sitting. It's really trying to figure out if a protocol description that works over the network is going to work correctly. And then later or separately, they'll worry about how to write software that correctly implements that protocol then.
And this is exactly what the Iron Fleet guys are doing too.
Yeah, so in some ways, I think the Iron Fleet paper that Butler described last Thursday really set out the big picture. There's sort of everything going on from the low-level code and concurrency or sort of multiple steps happening on a single machine, all the way up to reasoning about the protocol, and then finally a full system spec at the top level. And that's a good picture to keep in your head for like what's the grand scheme or sort of the whole thing that you want to achieve. And this paper is really tackling some intermediate layer in that Iron Fleet sandwich, if you will. And we'll try to figure out what exactly it might help with or not. And this paper sort of on top, like protocol verification is a subspace of verifying distributed systems. And then this I4 paper is even a sub-problem of that. And the thing they really look at in the context of verifying a network protocol or distributed protocol is this problem of figuring out an inductive invariant, which they claim is sort of the big deal if you want to verify a protocol. And it's probably one of the hard things you got to do, along with other hard things, to verify a distributed system. And one sort of insight we might try to extract from this paper is different ways to reason about the reachable states in a system. So we'll actually see that this I4 thing really has two ways of thinking about what are the reachable states in a system, which are the states that we need to prove some safety property about, some correctness property, and then sort of carefully translating between these two universes of describing reachable states lets them get some clever, cool results out of it. So that's the setup, protocol verification. And then we're sort of going to zoom in on these inductive invariants. So I just want to, maybe sort of repeat what Butler was saying last time about why sort of protocols are a hard problem to worry about, or distributed systems in general. This is sort of true even irrespective of verification and the kinds of sort of formal reasoning we're talking about in this class. There's sort of three broad categories I want to describe as like why distributed systems are difficult. One is the asynchronous network that is connecting the computers in a distributed system. So as we saw last week, there's many things that can happen in a network that make your life as a distributed system developer difficult. So your network might actually delay messages or drop them or duplicate them or corrupt them. And these are all sort of undesirable actions that lead to the fact that your nodes that are participating in a distributed system might have very different views about what is going on, which messages have been received. So you can receive separate different sets of messages in different orders. Messages might even be corrupted. I should say corruption is probably the easier things to deal with in this list. But nonetheless, this makes it difficult for the participants in a distributed system to agree on what's going on, because the network in the middle is kind of behaving in funny ways that is not immediately consistent across all machines. The second sort of class of problems that make distributed systems difficult is node failures. And here, what I mean is that you might have computers that are participating in the system that crash and then potentially restart and start running again. And one thing that Butler mentioned on Thursday as well is that one sort of difficulty in distributed systems is it's difficult to tell apart crashes versus delays or drops in the network. So if you are trying to communicate with some machine and it's not responding, it's difficult for you to tell whether your packets are just being delayed or dropped, or if the guy has crashed. And that turns out to be a source of some difficulties in designing protocols, and there's some impossibility results even that relate to this problem. And sort of more generally, the fact that nodes can fail can lead to inconsistencies between computers. So one computer was running, another guy crashed and restarted. So maybe he missed some part of the protocol execution. Now he has to catch up and synchronize his state and so on. So this is a very high level description, admittedly, of the problems in a distributed system, but maybe it's sort of good to orient yourself here. And the last problem that we're not really going to talk about at all in this class is, but sort of interesting maybe to keep in mind for yourselves, is for open systems where anyone on the internet can join, the question of membership turns out to be a hard one to deal with. So by membership, I mean, what are the computers that comprise a distributed system and talk to each other? And the reason this membership question ends up being sort of a challenging one is that if you have many participants, they might actually misbehave. And you might want to deal with misbehaving machines, like some guy joins a computer into your protocol and cheats in the protocol, tries to break the protocol in some way. And you want to design protocols that are robust against that. There's this whole line of work on Byzantine fault-tolerant systems, or Byzantine fault tolerance in general. Byzantine is sort of a technical term effectively here, meaning participants that can do anything at all, no constraints, completely arbitrary bad guys joining your system. This turns out to be indeed quite difficult, but we're not going to talk much about this class of problems in this class. You should take 6824 if this sounds interesting. Things like blockchains are worry about these problems quite a bit more. Anyway, so this is some context for sort of hard problems we're going to look at. Admittedly, as much as in verification, we're going to look at fairly simple examples to understand how we might verify anything. But these are the sort of bigger motivations for why we're doing formal verification here. So I want to start sort of to describe what is going on in I4 and what's sort of the clever thing they're doing. I want to start by describing this IV system, just to give you a flavor of where we are. So IV is this protocol verification tool developed by Ken McMillan and Oded Padon fairly recently. It's a pretty cool tool, and its goal in life is to really solve the problem we are talking about. It's really about protocol reasoning. So you have some protocol like the things that this paper talks about, CORD or Paxos or locking protocols over the network. These are the kinds of protocols that Ivy is sort of expecting to be good at. And the closest analog to this that we've already seen in the Iron Fleet lecture is the TLA protocol, or the TLA sort of way of logic. And we saw this in the Iron Fleet paper. And just to remind you what's going on in Iron Fleet is that, so here's a reminder of Iron Fleet from last lecture. At the bottom, we had code transitioning between code states. And then the Iron Fleet guys introduced this intermediate layer called the protocol layer. And this was also a state transition system. But the states at the protocol level weren't memory contents of their implementations, but really a more abstract description of what each computer in the system was doing. And then they proved that their code transition system really sort of corresponds to this protocol implementation. So we might sort of have these correspondence relations here that show that our protocol is our code implements the protocol description. And the benefit of reducing your code to a protocol is that it really summarizes the essence of what is going on a computer that other machines have to care about. So it helps quite a bit in dealing with the code. And then above the protocol, a very different kind of a proof happens in Ironfleet. In Ironfleet's case, this is done with this TLA logic. And they have a global system spec that describes how the entire distributed system operates as one logical state machine. And again, the picture looks similar. You have states and some transitions between them. And again, there's some sort of a connection here that describes how your states here correspond to the protocol level states. So that's the sort of end-to-end-ish picture from Ironfleet. And where this IV system sits and where TLA sits, it's a little bit sort of towards the top here. So IV is really sort of this connection. So this is what IV is doing for us. Oops, no dashed lines. I got a little bit excited about my dashed lines here. So IV is really sort of trying to tackle the question of showing that some protocol description in terms of transitions that individual machines might take could satisfy a specification for the overall system. So this is what IV is doing. And then I4 in this context is really looking at a slightly narrower problem. It's really trying to understand how this protocol is running along at the bottom here and what might be true. So one way you might think about it is that in I4, sort of this is where I4 sits. And it's really reasoning about protocol level transitions and trying to prove something about the protocol level transitions. But what I want to sort of describe here that I4 is not doing is that it's not really showing any kind of a correspondence between these protocol level states and some abstract version of that at the spec level transitions, or showing that some other transition system corresponds to protocol level steps. So I4 is sort of really sitting somewhere slightly above the middle of this Ironfleet sandwich here, and really helping us to reason more precisely about these protocol level transitions. So that's the context, that's the setup where I4 is going to sit for us. That makes sense? Questions about this setting, if you will? All right. So in order to get us a little bit more on board with Ivy, I wanted to look at a concrete, perhaps simple example of what Ivy is all about, because ultimately I4 is going to help us reason literally about Ivy code. So here's an Ivy example, if you will. So this is the lock service that, or the lock protocol that the I4 paper talks about. This is actually an example that came out of the Ivy examples that the Ivy developers worked on. So actually as far as I can tell, all or maybe most of the protocols that I4 verifies actually come out of the Ivy repo. And these are examples that the Ivy developers use to check Ivy or to demonstrate that Ivy is sort of great at verifying protocols. And the Ivy developers had to write some hints or some extra states, extra invariants to get Ivy to prove those protocols correct. And the I4 guys are basically showing that, hey, with this I4 tool, you don't need to write those extra things in the Ivy protocol description. And again, they're sort of focusing on sort of maybe this lower part of Ivy, not the full correspondence, but still reasonably cool that they're able to take existing Ivy examples and simplify them. All right. So here's this locking example. So what is this code even trying to do to give you a little bit more sense? So what this lock server is trying to represent is that there's maybe let me draw a picture that looks a little bit different. So we might have multiple servers. These are servers, not states. Server 0, server 1, and so on. And what's going on is that every server has a lock. and this lock can be held by at most one client. It's like any other mutex lock that you might have, except here it's in a distributed system, so only one computer can grab this lock at a time. So we have many servers, each with their own lock, and then we are going to have many clients, client 0, client 1, client 2, and so on. And the job of this protocol is to allow clients to grab locks. So what's going to happen is that this client might grab this lock, and by this arrow, I want to represent that client 0 is currently holding the lock of server 0. Hopefully it means no other client is holding that lock. And maybe client 2 is holding the lock of server 1. Client 1 is not holding anything. So that's the kind of protocol that we're trying to implement here. And you can imagine this is not going to be a super complicated protocol. You can just send a message to a server to grab a lock. And if it's available, the server will give it to you. And you can release it and put it back, and someone else can grab it later. So the way this is going to get represented in Ivy is just to sort of get you on board. Like we're going to say, well, there's a thing called a client and there's a thing called a server, and it's pretty opaque what that means. And then we're going to describe what the state of the system is. And Ivy, we'll talk a little bit about this later. Sort of Ivy's big contribution, if you will, is really automation and helping us prove these kinds of protocols with very little developer effort. And we'll see that actually it turns out the proofs for all these lock server protocols are quite simple, much less effort than you would probably spend in Coq trying to do similar proofs. So the state of the system is basically described by these relations. And the relations help Ivy automate this instead of writing some maybe more complicated state descriptions. And what's going on is that basically there's a semaphore relation, and the semaphore is just a way to describe whether a server is holding a lock. So the semaphore thing is basically this guy. So the semaphore relation is this lock or that lock on the server. And then we have this link relation, and the link relation is just describing these orange arrows. So if the link relation between a client and a server holds, well, it means that that guy is currently holding a lock. And like here's another link relation. And there's no link relation for the C1 guy. So that's just the terminology they chose to describe their state of the system. And it's totally described by these two relations, the semaphore and the link. And then on top of the state, in some ways, this Ivy system looks a lot like the story you've probably seen in every other paper in this class, where you have states, you have some initial states and a transition system. So here's the initial state. You start out with every server holding the lock. So there's sort of an implicit for all W here in Ivy, and there's an implicit for all X and Y in Ivy as well. So for all W's, all the semaphores are true. Every server is holding its lock. And for all clients and every servers, no client is holding any lock. That's the starting state. And then here's the transition system, or actions, depending on the terminology you've seen in different papers. This is exactly the same description. If you want to grab a lock, they call it connect. Well, there's sort of a slightly maybe artificial or logical operation here that says, well, you can only really acquire a lock if it's not being held by anyone. So in reality, the implementation would check for this, but maybe after some level of abstraction, which is sort of, remember, we're sitting in the middle of this code to top level spec sandwich. That level of abstraction, perhaps it's reasonable to assume that you can rely on some preconditions being true, like acquiring a lock already happens only if the lock is not held by anyone. And then you set your lock variable and you get rid of the server holding the lock, set the semaphore to false, and the opposite happens when you disconnect, which is a lock release here. And then these export statements just say basically these are the sort of top level transitions. Ivy can also have internal transitions, which we don't actually see here. And then sort of here's the safety spec, or like the total spec. In this sort of, in I4's view of Ivy, a specification is really a description of states that should hold true for all reachable states. So this is you can think of it as some kind of a safety predicate, if you will. And it's a predicate on these relations link and in principle semaphore as well. But it sort of makes sense to think of it this way because this link relation is the state of the system. It sort of embodies who is currently holding a lock. And the way to read this invariant, the spec of the system, is that, well, if you have one client holding a lock on a server and another client potentially holding a lock on the server, it's the same server S here, well, it's actually better be the same client. C1 is the same as C2. You can only have one client holding a lock, so you can't possibly have two clients. Otherwise, this would be false. So that's what sort of their correctness spec is for I4. Now, I should say, like, Ivy is a much more general system. Ivy, as we were sort of, let me flip to the previous slide, as we were showing here, Ivy really could show correspondences like this, where you can say, well, it actually corresponds to a transition system and in some limited forms, so like fancier things than just these safety predicates. But I4 is really focusing on a sort of maybe a lower level subset of Ivy, where you're trying to show just that some kind of an invariant, like the thing shown at the bottom of the slide, is going to hold in all the reachable states. So that's the sort of deal with Ivy. And our goal is going to be to try to prove this. So maybe as a concrete example, I actually went and downloaded and installed Ivy. It's a pretty easy to use tool, mostly written in Python. So fairly easy to try to use. So we'll look at that in a second. We can actually type this example into Ivy and see what happens and what goes wrong. To maybe set some sort of context for that, I wanted to first describe what's going to be happening in Ivy and what is Ivy going to be trying to prove, and maybe a little bit of why. So in Ivy, or at least in this I4 view of specifications being predicates about reachable states, what we really want to reason about is the safety of these reachable states. And this ends up being this inductive property that the paper talks about quite a bit, inductiveness being that like these safety properties are maybe going to be closed under this transition or action relation. So let me describe a little bit more what I mean by that. So this is going to be a slightly different view of this whole trace inclusion business that we've talked about many times already. Maybe it's interesting to see another take on the same thing, like maybe helps you understand what I4 is doing. So imagine, I should say I borrowed this idea from the talk that the I4 authors gave at a conference presenting this work. But it's, I think, a very nice way to think about what they're doing. So here's the state of all possible states. So these are all the states your system could be in. Any combination of those semaphore and link relations we saw in the previous slide, they're sort of, little bubbles in this diagram, states here and there. And then there are some special states, which is the initial state, somewhere in the middle here. And starting from this initial state, the system is actually going to start running. So you start somewhere, and then you take a step relation, the step corresponding to one of those transitions we saw described earlier. Either someone acquires a lock or releases a lock, and then you can actually keep stepping and discovering more states. So in some ways, like, maybe you might have loops, you can go off somewhere else. And eventually, what we really want to reason about to prove something correct is the set of all states that your system could be in. So all the traces or all the states you can reach in the code are described by starting from the initial state and stepping everywhere, anywhere you could possibly step. And you can sort of think of this as being, the set of all reachable states. Let me dash it and sort of, here's the set of all code states that we could reach that we want to reason about. I said code, but really it's sort of the, the protocol level code that we saw, the Ivy code reachable states. So these are the states we want to reason about, but they're actually a little bit hard to pin down, right? Like they're described only indirectly in terms of this step relation. So you start somewhere and then you keep going, and eventually maybe you reach all these possible states. That's the set we want to reason about. And as you've probably remembered many times in this class already, there's some bigger bubble here, which is the set of all safe states. So this is basically what the spec allows. Or in I4 terminology, this is the safety invariant. And the safety invariant is, in a sense, much better defined than the dashed bubble in the middle. The dashed bubble in the middle is defined in terms of this, step relation, and you eventually reach all the things in the dashed bubble. The spec bubble is a fairly direct statement. It's a predicate about the states in the bubble. So it's the statement that we saw on the previous slide that says if two guys are holding a lock, it's the same guy. So that very directly defines which states are in and out of this bubble. So there might actually be states that are satisfying that rule, but maybe they're not reachable for whatever reason in the execution from the initial state. For our lock server, turns out there's basically like one such state or a handful of such interesting states. But in general, like there's maybe many safe states that your implementation never gets to. And this is sort of another way of seeing this subset property that we've been talking about. So typically we've talked about traces of executions being a subset. So the traces of execution at the low level is a subset of the traces allowed at the top level in the spec. This is a set view of the same picture. Here's the states that you can actually get to in your implementation. Here's the states allowed by your spec. And if one is inside the other, great. The problem that Ivy is really struggling with, and I4 is all struggling with, is how do you characterize this thing in the dashed line? And the reason it's actually a little bit hard to characterize or sort of pin down this dashed bubble is sort of twofold. One is that, reachable states are defined in this very transitive way, so you don't have a closed formula that says, given a state, is it reachable or not? If we had that formula, we'd be actually in pretty good business. We could just like describe, here's all the reachable states. It's a formula. Does it imply the safety spec? Yes or no? That would be really nice. The problem is that these reachable states are really defined in terms of where you can get to after an arbitrary number of steps. And that's really what makes this job difficult of pinning down this dashed bubble. And so that's one thing. It's like difficult to pin down the dashed bubble. The other problem on the other flip side, this like solid line bubble, the safety spec bubble, it's well defined, or the spec set. It's well defined in terms of being a direct predicate on the states inside the bubble, but it might not be inductive. And this is the big deal that the paper makes about invariance, is that there might be states inside of this safety bubble that by themselves satisfy the rule, like no two guys hold the same lock. But if you just blindly pick that state and you start running from there, you might, maybe things will go fine here. Maybe you'll, make some step transition and go to another state that's also safe, or maybe you'll take a step and you go to a bad state. Now, this is not necessarily the end of the world. It doesn't say that our implementation is broken because this is not a reachable state. You could never have gotten there. It's just that this spec bubble is too loose. It allows states that, because you could never get to, they're sort of not constrained enough. And if you really start executing in this unreachable state, you could get nonsense results like escaping out of the safety bubble. So these are the sort of the two difficulties here. Like one bubble is precise but ill-defined, and the bigger bubble, the spec bubble, is well-defined, but it's not tight enough for us to prove that you can execute and keep staying safe. This is the inductive notion that the paper talks about. So hopefully that makes sense. Any questions about this sort of way of looking at this? It's a mathematical level. I think I'm not saying anything new here, but perhaps it's helpful nonetheless to look at the same thing from a slightly different visual perspective. All right. And sort of the usual story that, again, we've told you guys several times, is that the proof plan here for how to deal with this difficulty, at least in Ivy's case and in many other sort of unbounded systems, is to actually find some kind of an inductive invariant. And the way to think of it is that we're going to have some other, boundary in here that sits between the very tight but ill-defined dashed bubble that defines all the exactly reachable states, and also between this spec bubble that is also well-defined but too loose. So this light blue line is some kind of an inductive invariant. This is the thing that I4 is really trying to come up with. And the cool thing, the reason it's going to help us make the proof go through is that it should be inductive, which means that any state that you have in this blue bubble stays in the blue bubble if you take a step. Might not be reachable, but it's constrained enough that it stays in this light blue bubble. And maybe it like goes and reaches a state that really is executable and reachable there or not. But the important thing is that this light blue bubble in the middle, this inductive invariant, is closed under steps. And this is going to make our proof much easier for unbounded traces. This is what Ivy is really relying on. Make sense? Questions about what's going on here? All right. So for Ivy, the proof plan is sort of twofold. Again, just to remind you, this is all about the safety of reachable states. And there's two things going on. One is that we need to prove that all the initial states satisfy the invariant. So for any state in that initial category, well, it better be the case that the invariant holds on that state. So whenever you start out, you're going to be in, like, all the initial states are in that light blue bubble that we saw on the previous slide. And the second rule here is that whenever you have two states, basically you go from one state to another state S prime, well, if the invariant held on the starting state and you can actually step from state S to S prime, well, then the invariant has to hold on the new state where you got to. So this state, this sort of first requirement says you started out in this inductive invariant bubble. And the second statement says that this guy is actually inductive. You pick any state in the bubble and then you step and you stay in the bubble. And the way to think of this is that this invariant is really an over-approximation of the reachable states. And using this over-approximation really allows Ivy to reason about these potentially unbounded executions. Because notice that here, there's basically like two rules you got to check. Are the initial states satisfying the invariant? And does every transition preserve the invariant? And just these two rules let you check arbitrary sort of length traces because you can actually do an inductive proof on them. So that's the really cool thing, but you need to cook up this over approximation of the reachable states that are embodied in this inductive invariant. So let's try to actually look at the concrete Ivy tool, just to give you a flavor of what this looks like. So let me switch over to a terminal. So here what I have is the lock service that you just saw on the previous slide typed up in a file. And I can actually run Ivy on this tool, on this sort of protocol definition. So I can run Ivy check over here on the lock server. And what it's going to do is it's going to actually just try to check those conditions that we saw on my board just a second ago. So what you can see is there's some sort of technicalities here that are not maybe super important for us, but here's the first thing it checks. The initialization establishes the invariant. So it checks whether our init code produces states that satisfy our invariants. The invariant that we see at the bottom left here is that indeed no two guys are holding the same lock. And sure enough, that's true of the initial state because no one's holding any locks. Easy enough. And then we got to check that all of the transitions preserve the invariant. If you start in a state that satisfies the invariant, you take every possible transition and you see if you end up in a good state. And it turns out one of our transitions fails. So let's see what the heck's going on here. So this is actually having to do with this non-inductive invariant business that the paper talks about, and we were sort of talking about on the previous boards as well. So let's try to understand what's going on. So here, what Ivy is telling us is that if we take the connect action, so this guy over here, then we can start from a state that satisfied the invariant and somehow end up in a state that violates our invariant. So what's going on? How can this happen? Why is our invariant not inductive? Anyone have a guess from the paper or from looking at this code? What's wrong?
I guess the invariant just says that if C1 and C2 are linked with S, then they have to be equal. But before you do the link XY becomes true, you don't know whether it could be the case that there's some other client that is linked to it, and when you run that statement, when you run the link XY becomes true, you'd have an obligation to prove C1 equals C2, but you wouldn't be able to, I guess.
Yeah, so I think what's going on is right, like, so the invariant says that you can never have two clients holding the lock. But what the invariant is sort of forgetting to say is that it's also actually going to be quite bad if you ever have a client holding a lock and the server still thinks that it still has the lock as well. That's sort of a precursor to getting you to violating the safety invariant that we really have stated here. So the safety invariant is maybe what you care about at the end of the day, but sort of one step before the safety invariant, you could be in this bad state where client one is holding a lock and the server thinks no one's holding a lock. I have also the lock. So then some other client can come in and grab the lock, and that's going to violate your invariant. I think that's what's actually going on here. That's why Ivy is not letting us actually check this protocol. So we can actually strengthen the invariant. This is what the I4 paper is talking about, that sometimes you got to write extra stuff here to make your invariant more inductive. So one way to think of it is that the invariant line we have written down here on the screen is that big dark blue circle. That's our spec bubble. And what I want to do is actually kind of shrink it to have a tighter bubble that is still, of course, inside of the safety bubble. We're only going to add extra constraints. We can't make it unsafe. But what we're going to do is add constraints that make this whole system closed under these actions or transitions. So the rule we were just talking about is that we want to say that if one client is holding a lock, then actually the server better not think it's holding that same lock. So the way to write this in Ivy is I think you just write down another invariant. So what we can say is, like, if some client thinks it's holding a lock on a server, then arrow, the server is not holding a lock. So semaphore of the server better be false. So I think this is sufficient. We can go over to the right and try to check it. And yeah, it's cool, sure enough. So now our stronger invariant is also established at initialization time. It's like a slightly non-trivial thing. It's like, well, we strengthen the invariant, but all the initial states are inside the even stronger invariant at start time. And then both of the invariants are preserved by the actions in this protocol. And there's something cool. Okay, so like, first of all, this hopefully gives you a sense of, well, here's what this I4 paper is talking about. Developers in Ivy are probably looking at text files that are more sophisticated versions of the thing you see on the left here, and they're having to state these extra invariants. Here it was fairly straightforward. I think we cooked up what was wrong fairly quickly. But in general, if you have a more complicated protocol, there might be extra constraints about, well, why aren't you going to get to a bad state that are more difficult to state? And this is what the I4 paper is really trying to do, is to synthesize that last line you see on the left of the screen, so that I don't have to be so clever to figure out that's how I got into trouble. The other thing that's really cool, actually, that's like a little bit almost an aside, is we're just not writing any proofs here at all. I just ran this tool on the right, and it checked everything for me. So in fact, it's actually super easy to add extra actions. So just for fun, let's try to add an extra action where one client, instead of releasing the lock and giving it back to the server, is going to sort of transfer the lock to a different client directly. So instead of releasing and having a different client grab it, I'm just going to have a client-to-client transfer of a lock. And fairly easy to write this in in Ivy. So some kind of an action, I don't know, swap. So here we have X client as the guy who's going to give the lock. And here's another client, Y, who's going to get the lock. And we'll have Z be the server. And the way to write this in Ivy is that we just have to remember what the link value was of the guy who's donating the lock and give it to the guy who's getting the lock. So we can do something like var a bool, and we'll have two booleans. We'll save the link value of the X client, and then we'll save also the other guy, and we'll sort of swap. So X is holding the lock. X is holding the lock as if it was Y before, and Y is holding the lock the way that X was holding it before. Maybe that's a slightly strange phrasing, but the way to think of it is that imagine X was holding the lock before, so A was true, and Y was not holding, it was B. So we're just going to swap these link variables around. So whatever X was holding becomes Y's link variable, and whatever Y was holding becomes X's link variable. So here's a transition, probably not super complicated, but you can use Ivy to check that it's still a safe thing to do. So I can rerun Ivy on the right side here, and it checks an extra transition. Oh, it doesn't check this transition yet because I forgot to declare that it's an external action, export swap. And now if I rerun Ivy, well, it checks that this extra transition also preserves the invariant, and the whole thing satisfies our safety spec, if you will. So the one really cool thing, that's like not so much the point of necessarily the Sci4 paper, but like Ivy is actually pretty cool here. It's able to check protocols without any proof. You could imagine that doing the same thing in Coq would have required quite a bit of typing of LTAC and lots of symbols going on. Here, quite a bit of automation going on. All right, any questions about sort of this concrete Ivy demo? Hopefully makes some sense, or maybe makes some things more.
Amanda has a question.
Oh yeah, can you read it? I like, the Zoom Linux client doesn't let me see chat comments.
One question, does this not protect against deadlock?
Yeah, so remember, well, invariants, or the kind of spec that I4 is excited about, is this invariant spec, meaning what is true about all the reachable states. And that's just a safety property, meaning that you never get to any bad state. So in a sense, deadlock is a perfectly great outcome if you want to prove a safety property. In fact, if you deadlocked right away in the initial state, things are just so nice. You can never get to a bad state because you're just stuck there in the initial good state. So that's sort of a depressing way of looking at it. But like, so safety properties are really very happy to see deadlock. On the other hand, liveness properties are where you might worry about not making any progress because you deadlocked. Ivy, as far as I understand, it doesn't really check for liveness properties, although I haven't read every single Ivy paper. There's quite a bit of work on Ivy. That's beyond what I4 is using. But indeed, deadlock is usually not a safety failure.
It's actually a little bit more subtle than that, because it's true that if you just look at the external behavior, deadlock is a liveness property. But of course, if you look at the internal state, typically the way you get deadlock is by having every process waiting on something that's waiting on something else in a loop. And that is certainly a safety property, because if you look at the internal state, that's a bad internal state. And I believe this distinction is a source of a lot of confusion.
Yeah, I should apologize. Indeed, so Butler is right. So what I really was, I think my statement might have been more accurate if I was talking about live logs, so a state where, something is happening, but just like nothing useful is happening. But Butler is right that like deadlock, you could detect that in principle. You look at a trace and the whole thing stopped. Well, that's a very concrete trace where no one can make any further transition. You enter some dead end state and you could decide that that's bad.
But of course, that's going to be an internal state.
Yeah, I guess it depends on how you model your transition system. I could imagine that you could decide, you could write a transition rule that says if no one can take a step, then you enter a bad observable state. But sort of depend. Yeah, you could probably formulate it so that you make the deadlock state a visible external action.
Yeah, that's absolutely right. And in fact, if you look at how people don't do this in operating systems, but in database systems, they have what are called deadlock detectors, which do exactly that. They monkey around in the internal state to figure out when the internal state has gotten into a deadlock situation and make that externally visible.
Yeah.
Okay.
Ivy also does have liveness verification.
Thanks. Yeah, I knew I was going to be bitten by that.
Yeah. It's not completely general, but it does something fairly sophisticated where it reduces liveness to safety.
Huh? What does that mean?
Some sort of model checking thing that I don't understand. They reduce checking to looking for, they reduce liveness violations to looking for a fair cycle. That proving the absence of fair cycles. This is what they say.
I see. So
I don't know
some
how
kind of a
works.
sufficient condition that guarantees liveness.
Yeah. So in some cases, they can take a liveness property, turn it into a safety property, and then prove the safety property. I think they did this for the that SOSP paper on the Stellar consensus protocol. I think they did this.
Interesting. Yeah. Well, as you can sort of tell, right, like there's sort of Ivy, the tool, which is much bigger than what I4 is using, or that what I4 is really able to directly help with. And then sort of I4 really has this somewhat narrow view of what correctness could mean for them as just a safety predicate. But yeah, thanks for the good question about deadlock. Yeah. Any other questions? All right. Okay, so just to maybe give you some a little bit of a flavor, like why does this automation work out? So one thing that's going on behind the scenes in Ivy is that sort of it takes this Ivy code and that we are writing and sort of seeing on that screen and really turns it into these constraints for a SMT solver called Z3. And Z3 in general, lets you state all kinds of things. You could, in principle, I think, even state close to all the things you could, state in Coq as well. But Ivy is very careful to not let you sort of shoot yourself in the foot and make something that Z3 has trouble solving. So really, Ivy has a very restricted or somewhat restricted logic, depending on who you ask. There are some constraints on what kinds of things you could state. So there are sort of limited use cases where you can use an existential quantifier, like saying it exists some state. There's some limits on the kinds of predicates you can say. You can't have some high order predicates and so on. But the upshot of all this is that if you have these restricted Ivy statements, then they lead to Z3 constraints that Z3 can always solve. That's a really cool thing. That's why, in that terminal, I was able to run Ivy check, and it always gives an answer. It either gives an answer saying, well, you have a broken invariant, or says, okay. And Z3 can actually efficiently check these conditions, 1 and 2, that we see on the left here, and give answers. And sort of the cool thing is that it's automated, but it's really doing this automated proof for arbitrary states, right? Like it's any initial state and any transition, and there could be millions of clients and millions of lock servers, and this proof would still hold. So it's really an unbounded proof in that sense, or proof for unbounded states. And really what, unbounded state proof, maybe that's a better way to say it. And it critically relies on this over approximation of reachable states by the invariant. Having this closed formula describing the reachable states in the invariant is absolutely the key for why this automation is able to make a proof that holds for an arbitrary number of states. So that's really the core of Ivy, why sort of it's able to do stuff that you guys are struggling to do in labs, for example. Not necessarily the same thing, but there's no complicated LTAC proof in Ivy, even though it's also talking about complex, potentially protocols and arbitrary transitions. Make sense? All right. So that's the Ivy world. And then there's sort of, okay, and the Ivy world really relies on this invariant to describe reachable states. And then there's a different world that I want to contrast with, which is this model checking world. And model checking is also a strategy for checking the safety of reachable states. But it works in a rather different way. So instead of having those two conditions that rely on an invariant, this model checking plan really is sort of feels like a little bit of a brute force plan. So the way model checking works is you take your initial state and you just see where it goes. You try to take a step and you get another state, S1. Well, maybe you take a step from S1 and you get to S2. And then you go back to the initial state. Let's take a step here. Here's S3. Well, maybe a step from here gets you back to S2. Or maybe there's also a step to get to S5. And you sort of explore this, graph of all the possible transitions. And they don't have to necessarily go to the right? Like you can have loops that go back and forth, and there's some graph of reachable states. And this is really literally exploring that graph of reachable states that I was showing very early on in the dashed bubble. These are the very tight set of reachable states, no over approximation involved. Of course, the problem is that if you're so literally exploring these reachable states, you're going to have a hard time enumerating them if your system has an unbounded state size. This is this thing I was just harping on the previous board, that Ivy is proving this safety for arbitrary reachable states that satisfy the invariant. This thing is only really going to work out if your state space is kind of small. So in particular, here's an example. Bounded state sizes. Imagine that we are going to run this lock protocol with maybe one server and two clients. Very small scale compared to sort of the unbounded size that Ivy can do. So we'll have client C0 and client C1. And the state of the system, if you recall, is really defined by those relations. So we have the relation, the semaphore of S is the server holding the lock. And then we have the link relations that say whether a given client is holding a lock. And we have that for, all of our clients, including C0 and C1. So how does this model checking going to work? Well, we'll start with the initial state. The initial state says that the server is holding a lock. That's true. And no client is holding a lock. These are all false. That's the starting state. And the way we're going to explore is we'll take this starting state and try to apply various transitions. One transition is that the first client gets the lock. So here's a different state. Another transition is this guy can release. Well, actually, if you release, you go back there. Another transition is that we go from the init state and a different client grabs the lock. So now the server is not holding a lock, and instead of the first client holding it, the second client holds it. As far as I can tell, these are all the states for this little 3 sort of machine, one server, 2 client example. The only thing that can happen here is they can give the lock back. So you can sort of have these transitions, and that's it. That's the entire system state diagram for this little universe. And you can look at this and you can convince yourself that actually, indeed, this thing satisfies the safety spec. Because the safety spec, if you recall, is a property of the link relation. No 2 clients can ever be holding the same lock. And sure enough, here's all the reachable states. There's never a reachable situation where here's a true statement in this column and a true in the other column as well. So that's a safety spec. And indeed, this bounded system is safe. And you can notice, actually, the safety spec doesn't really talk about this semaphore column, which is sort of the missing part to make this inductive invariant. And you really need to involve this semaphore column to cook up an inductive version of an invariant that holds, that sort of would let us do the kind of proof we saw in the Ivy case. Now, model checkers in general don't worry so much about describing reachable states with invariants the way Ivy does. But it turns out, sort of like where this paper came from, as far as I can tell, is that 6 months before this paper came out, or very shortly before, some of the co-authors developed a model checker called AVR, just an opaque name, roughly speaking. And what AVR does is when it runs, it tries to synthesize some kind of a concise predicate for all the reachable states. And this is sort of described in the AVR paper that I4 is citing, and somewhat sophisticated thing going on there. We didn't read it for this class. But I think what's going on, the reason this model checker AVR is trying to do this is that turns out to be an optimization for them. So it turns out that for AVR, as far as I can tell, it's more efficient to explore all the reachable states if they can cook up a predicate that describes what are all the reachable states. And of course, you can always, in principle, explore all the states first and then say, well, the predicate is, it's one of these states in this big matrix. That's true enough. It's a predicate that describes all the reachable states, but it's pretty big. And the cool thing that AVR is doing is it's really trying to collapse this down and trying to write down a simpler formula that in AVR's case, I think really leads to AVR being a more efficient model checker. But it turns out, here's sort of the really cute thing that I4 is doing, is it leverages this compact formula that AVR cooks up, and it tries to sort of use that formula for Ivy. And what you can see is, like in Ivy's case, what we were really lacking was that intermediate bubble and over approximation of the reachable states that was embodied all in one formula instead of being described by this transitive set of jumps between different states. And what's going on in AVR is that AVR is able to reason precisely about all the reachable states because it just reaches them. Literally, it explores this graph you see on the left of the board. And then it is able to get a very precise predicate of that describes all the reachable states for its bounded instance size. So one server and two clients, perhaps. And then sort of I4's clever trick is, roughly speaking, to take this AVR predicate and sort of transform it into an Ivy invariant. That turns out like there's some heuristics or a couple of guesses or transformations involved in that, but it's actually, I think, a fairly straightforward transformation at some level. Much of the action actually happens in AVR, as far as I can tell, where the predicate, this is the compact predicate, is getting synthesized. And the insight is that if you can synthesize a compact description of what states are reachable at a small scale, the same compact description might actually work for an arbitrary scale as well. And that's what Ivy is doing, or so that's what I4 is doing. Maybe to describe I4's workflow here. So what happens in I4 is that you start out writing some protocol in Ivy. And I4 takes that protocol description and cooks up a small version of that guy that limits the number of clients, the number of servers. And I think it basically guesses some small limit, like 1 or 2 or 3 for every one of those things, 1 server, 1 client to start with, and so on. And then it has this finite version that actually not only is finite, but also is now written in a language that AVR, this model checking tool, can understand. So it transforms from an Ivy description of the state transition system into both a bounded instance and written in AVR's format, and then feeds it to AVR. And AVR like its sort of goal in life was really to model check this description of a finite system, and it's going to say yes or no. So maybe it'll just find a bug in your protocol right then and there, and then I4 will say, well, your protocol is buggy even when I reduce it to one server and two clients. Or AVR might say, yeah, your system is great. And sort of almost as a side effect in AVR's case, it spits out this description or like a predicate of reachable states. And it turns out this predicate of reachable states is useful not just internally in AVR, but I4 is going to use it. So I4 takes this guy and basically does a little bit of rewriting just to get this finite predicate that AVR used to describe its finite states to a predicate of, unbounded states. And sort of the fact that it's a predicate over the reachable states hopefully makes it inductive. And the hopefully part is checkable, right? Here's the cool thing. Ivy is really nicely decidable. So you don't have to ask a developer, hey, go try to write some cocktaxics, try to prove it. You could just have I4 give this to Ivy. So then maybe the output is Ivy runs on this. So you add this extra inductive invariant and Ivy maybe says, okay. Or maybe if Ivy doesn't say it's okay, well, somehow, that's not the right, inductive invariant. That's not the right over approximation of states that's going to get you the proof to go through. So, okay, try a bigger size. So that's basically what the paper is talking about, bigger, bounds. So instead of one client, try two clients or two servers or three clients, and try to explore it until this terminates. So that's roughly what this I4 clever trick is, if you will. Make sense? Questions about this? All right. So one thing we asked you guys in the reading question was to try to think of like what's the relation between this and concurrent software. So if you recall, Armada in some level also looks similar, right? Like it's a state transition system. There's concurrency. Many actions can happen at once. And somehow, in Armada's case, this is not the approach they take. It seems to work reasonably well for I4 and IV proofs. But do you think this is a sensible thing to do for Armada? Could you do take the state transition system for the Armada lock-free data structures and apply similar ideas to make that work out? Or do you think this is going to fall apart for some reason? So I'll give you guys the next maybe 10 minutes to chat in breakout groups about this and see if you come up with some interesting insights. And then we'll see you guys back here in a little bit. Any questions before we send you guys out to breakout rooms? All right. See you guys in 10 minutes. All right. I think we have everyone back. So what do you guys think? Could this work for something like concurrent software in Armada? Anyone want to jump in, go first? I should admit, actually, I'm not sure I have a crisp answer myself for what is the deal. Like, would this work? Maybe it's an interesting thing to try out, but seems like an interesting thing to speculate on, maybe to get a better insight as to what is this technique really getting at. So anyone from the first group want to go? Amanda or Caleb or Julian?
I guess what I had said was that we would need to have a stronger invariance like we do in I4, but then we were talking about how do we assess the strength of a given invariance.
Yeah, so let's see. Yeah, so maybe one thing that's going on is that Armada itself is not really built on an exhaustive model checker the way maybe there isn't sort of an obvious exhaustive model checker like AVR that you could use. So you'd really need to sort of cook up a new tool that translates Armada source code into maybe AVR transition system and see if AVR could execute all possible executions of your concurrent software. So that'd be one sort of thing going on. one potential problem there, right, is that maybe there's a lot of different reachable states because of the concurrent threads that are going on, although a little bit hard to speculate depending on how you encode it. Maybe the non-determinism of concurrent threads is you could get it to be encoded in a way that's similar to the non-determinism of which action to take at any given time in Ivy. So maybe that's okay. Yeah. Any other thoughts from your guys' group, Caleb or Julian? All right.
Caleb has a comment. He says,
oh, yeah.
He's not on his mic, but we're talking about potentially applying the invariant generator to determine the next refinement level, but it's possible that this is too big of a jump in refinement levels for the automatic proof Armada uses between levels.
Ah, interesting. Yeah. Yeah. So there might be actually clever ways you could actually use this stuff to maybe not do the full proof, very much like I guess I4 is not doing a complete proof either. It's just like helping you figure out the invariant. But yeah, perhaps some tool like I4 could help you guess where to go with the next level in Armada. That's an interesting thought, yeah. So how about the second group, Eileen or Jenny or Upamanyu?
So I guess we talked about, I guess one thing we talked about was the similarity that Armada's invariance already has with the way Ivy works, in that the way it'll try to establish the invariant is by just making an obligation to show it holds on the initial state, and then obligations for each of the different step types to show that it maintains them, which is a lot like the Ivy example that you just did earlier. And I guess we're trying to figure out, as you know, I guess the third I or whatever, the inference part of I4, we're trying to figure out what exactly inference would look like in the Armada world, and what a smaller instance would be of some larger parameterized program or something like that. And for example, with the one lock-free data structure that was actually checked in Armada, I think it was single producer, single consumer anyways, so there isn't really any parameters for how big it is. It's just one thread and two threads, I guess. And so I guess it seems like you could apply model checking to it on its own, like you said, but I'm not sure what you can really infer in the way that I4 works by using like small and large instances and stuff.
Yeah, so you're right. I think there's a difference in the, well, it depends on exactly the kind of code you're talking about. If you have a piece of code that involves lots of threads, then maybe brute force model checking in Armada would require lots of threads to be considered at the same time, whereas in I4, maybe you can concretize it to a finite thing that got like 2 threads or 3 threads total. So maybe that'll work. But you're right that for some Armada examples, there's really not a parameter choice to go. And you could imagine handing this off to AVR as well in principle. So as far as I can tell, like, this is a little bit fuzzy. I got to say, I don't fully understand where the magic happens between IVR and I4. I think the sort of cooking up a small formula describing the reachable states is really something AVR is doing for the most part. And I think it's going to be mostly a question of whether AVR is able to cook up or synthesize a predicate describing the correctness of a producer-consumer queue in Armada. Seems like maybe a bit of a stretch, because the sort of complexity of invariant might be kind of high. We were talking with Butler here during the breakout as well, and we were sort of trying to think of this AVR thing as a kind of program synthesis, where AVR is trying to piece together all the various, syntactic constructs that could go into forming this concise predicate, and then checking, well, does this thing work? Does this thing work? And it's a little bit of an open question, I think, for us, and like maybe more of a question about this AVR tool, whether it'll be able to synthesize a syntactic formula describing the reachable states for a producer-consumer queue, say, or some other concurrent data structure. And like the evidence is kind of mixed from the I4 paper, right? So they tackle a couple of examples. Sometimes it works well. Sometimes it just outright fails. And it's not entirely clear what is going on. So like they say, well, runs out of memory in this AVR tool, which seems to suggest something really non-scalable is going on there. And not just the states, but maybe the description of the states itself is kind of a complicated thing. hard to write down this formula or try all possible formulas to see which one sticks. So yeah, like hopefully this was an interesting thought exercise. I don't think, again, to restate, I don't think we have a crisp answer. In some ways, maybe an open research question, whether you can do this or not for concurrent software. And maybe not enough data in this I4 paper to really say one way or another. But hopefully helps, try to think of what this idea is and where it might be useful or not. All right, so that's all the time we had for this I4 paper today. Thanks for coming. See you guys. I guess there's a hacking day nominally this coming Thursday. What's really going on is actually all the course staff are attending a conference, systems conference, OSDI, so we can't make it to lecture. But see you guys next week then. Have a good one.